Well, hello, Stat 152 students. Welcome back to class. I hope that you've enjoyed your break and you were able to catch up on some sleep because it looks like you're going to have a lot of work to do now that we're back in school for the next 5 weeks. So I wanted to give you a quick reminder of where we are. We had started to talk about the concept of something called a random variable. And I apologize, my handwriting is not going to be great because this is my first time attempting to use this Blackboard function on my brand new laptop, which I had to buy in order to do all of this online stuff. We started to talk about the concept of a random variable. We actually started with the idea of an algebraic variable. And if I don't know if you remember, but when we were talking about an algebraic variable, we talked about it in terms of being a teacup. So we talked about little x being kind of like a teacup, and you don't know what numeric value is going to go in there, but you know that some sort of number might go in there. Just like in a regular teacup, you might have orange juice, you might have tea, you don't know what you have in there until you actually look inside. So an algebraic variable is like a holder for a single number. In contrast, a random variable is something a little different. Random variables we're now going to denote with a capital X. And there are two possible values that can go with a random variable. One is the actual numeric value that it could take, and one is the probability that your random variable is going to equal that little numeric value, whatever it is. So if you recall, algebraic variables, one value, random variables, two possible values. So having done that, let's now take a look at what we learned about prior to our extended break, which was the discrete random variable. Here we go, discrete random variable. And we learned about a discrete random variable first in the context of a table. So we would have all the possible values that x could take, and then we'd have all the probabilities that went with those values. So for example, maybe I have an x that takes the values 0, 1, 2, and 3, and they might have equal probabilities of taking those four values. Now the trick was to make sure that the sum of all your probabilities equaled 1, and that each of these is between 0 and 1 inclusive, right? As long as that was all true, then we got to call this the probability distribution for our discrete random variable. There we go, probability distribution. And that's kind of cool. So we learned how to do all of that. We created a bunch of those tables, and we said that was well and good, but there were certain forms of a discrete probability table that we end up using over and over and over again. So we actually went from this concept over to an equation. And we specifically did that in the case of the binomial distribution. Don't know if you guys remember that, but in that case, we were able to find the probability that our random variable equals some value is equal to n choose x, p raised to the x, 1 minus p raised to the n minus x. And we explained how you could go back and forth between these two forms when you're talking about a discrete probability distribution. Well, we're about to launch into a whole new world. We're now going to be looking at continuous random variables. And by movie magic, I now have a blank slate, because the thing about continuous random variables is that you're going to have to understand a little bit about calculus. Now, do not panic. Those of you who have taken calculus will know what I mean by integration. Those of you who have not, I'm about to teach you what integration is. All integration is basically the area under a curve. And believe it or not, you already know how to integrate. And let me demonstrate for you. Let's say I had a straight line across here on an xy plane. Let's say it ran from 0 to 2. Let's say it had a height of 1. So remember, this is your y-axis, this is your x-axis, and basically all we've done here is draw a rectangle. But here is my line. This line is y equals 1. And let's say I asked you to tell me the area under that curve between 0 and 2. You already know how to do that, whether you realize it or not, because this is of length 2, this is of length 1, 2 times 1 equals 2. So the area under the curve in this case is 2. All right, this is a very simple case, but there are a couple of other cases that you already know how to do. The point is that this concept of the area under the curve seems like it's very complicated, but it really is very simple at its very heart. Again, creating an xy axis, let's say I put a half circle on there. and I wanted you to find out the area under this curve. Well, if this half circle has diameter 2, that means it has a radius of 1. We know the equation for the area of a circle. It's pi r squared. So in this case, it's pi times 1, which is just pi. And then because this is only a half circle, we would do pi divided by 2, and that would be the area under this curve. So as long as I keep my curve a reasonably simple geometric shape, you all know how to look at the area under a curve. What's going to happen when we encounter continuous probability distributions is something like this. I'm going to start by teaching you about the normal distribution, and in fact that may be the only continuous probability distribution I explicitly teach you about. And I'm going to talk to you about the probability related to the normal distribution. Now for the discrete random variables, I could explicitly tell you a probability for a specific value. It turns out for continuous distributions, that's not really possible. So what we're going to end up doing is looking at the area under the curve within certain sections for certain values of x. For instance, this might be x between -1 and 0. And the probability that x is somewhere between these two values is going to be calculated by the area under the curve. Now don't panic, we're not going to make you do integration to do that. I just wanted to make it clear that this idea of area is something that is intuitive for you. You already know how to do that if we're talking about a simple geometric shape like a rectangle or half of a circle. Just because we've gotten a more complex shape doesn't mean that the basic idea isn't the same. So that's a brief introduction to integration. Woohoo, and you can now all say that you know calculus. Yay! At least the very simplest form of calculus. And we're going to take that knowledge with us as we move forward into our slide sets about the normal distribution. That will be next. See you there.